Hello everyone, my name is MAHDI SHOOSHTARI and I'm the data scientist and lead developer at Canoe. I'm interested in research fields such as computer vision, machine learning, and big data. The increasing availability of data with high spatial and temporal resolution from satellite to street-level images present opportunities to make use of machine learning to drive and describe characteristics of the built environment regionally and nationally. Once produced, these metrics are themselves large data sets with data on 800,000 locations over multiple months and years. This presentation will provide illustrative examples of Canoe's approaches and tools for working with very large data sets to produce metrics of urban form useful for environmental health research. The first powerful tool that I would like to mention is the Google Earth Engine. Google Earth Engine was introduced in 2010, and it's a tool it can be useful for two main purposes. One is for curating and managing historical and ongoing satellite data, because they have the big data sets of satellite images from 1980 forward, and also it's a tool for easy to use an analytical platform for implementing algorithms using JavaScript to process the data. One of the data sets that we have developed and extracted using Google Earth Engine is nighttime light, that we extract all the values for all the postal codes in Canada for all the available years. We also use Google Earth Engine to extract NDVI from satellite images. We were mainly interested in MODIS and Landsat satellite because they had different resolutions. And we could also develop monthly MODIS data. For the nighttime light, we could import the list of locations and extract the value for all those locations directly from Google Earth Engine. Here we use another approach. We downloaded the raw data for all the raw data means raw satellite images, and then I calculated buffers around each postal code using MATLAB script. The buffers for Landsat are for 100 meter, 250 meter, 500 meter, and 1 kilometer around each postal code. And for MODIS, it's for 500 meter and 1 kilometer around each location. The other usage of Google Earth Engine for us was to develop Lcz values. So we create the training areas in Google Earth Engine. We either import the train areas into Google Earth Engine or use the training areas that we develop again on Google Earth Engine. And after applying image classification on the Google Earth Engine, that these methods are already in there, we could get the final results again from by either location or the images for further processes. On the other hand, we can use Google Street View images that give us that contains a range of new information that can be used for mapping macro-scale urban features. And the interesting projects that we are working on currently is for example, detecting the buildings and realizing the building and calculating the building heights or the type of the buildings, or for calculating the vegetation cover in each Google Street View image for each location, or the type of vegetation that might be interested for the different researches. As another approach, Tripedia MIT research group came up with a green view index that we could also implement the same approach. And we have the values for all locations in Canada based on this approach. The way that we use it, the main idea is that they count the number of green pixels and based on that, they see how green each location can be. They use two approaches. For first one is very fast but not very accurate. We implemented this approach for all the locations. But the second one, which is more accurate, takes a lot of time. So it can be done for custom requests for a small sets of locations. So right now we are exploring new deep learning based approaches, which are not only just for the greenness. For example, we are interested to know how we can determine local climate zones for each location just by looking at street level images. So for a better understanding about each location, we want to have a panorama view. So for each location, we use 6 horizontal images all together. And we use image classification to predict the local climate zone of each location using Google Street View images. And we got so far to the accuracy of 80%, but it's still a work in progress. And for that, I developed this image classification using TensorFlow and Python programming language. But in general, for evaluating the accuracy of machine learning approaches, or in general any other algorithms that might be used, we need to have a good training data. And there are many approaches out there. One that I would like to mention today is that I've developed a custom interface that can use the Google Street View and satellite image at the same time, so that the user can can use both these images and have a better understanding about the label that he wants to have for that location. In our case, the label is the type of the local climate zone that location belongs to. For this interface, I use HTML and JavaScript. As under work that it's pretty much done, we are designing a data website that has all the available data sets that we extracted or developed online. And the user can see and zoom in and zoom out to have a better understanding about the values and its relation to the locations. And also, as I will see in the next slide, access the data through the website. This part of the job is done by Andrew Redivo, our GIS and web expert, and he used GIS, PostgreSQL, PHP, and Mapbox. As I said, after you log into this website, if you have the permission, you can download the data based on selecting the category. For example, category can be the greenness, the group can be Landsat, the variable can be, for example, buffer around 250 meter kilometers, and the user can also select the interested years and the provinces, and then the data, he can download the data as CSV file or other type of data available. I also developed some custom tools based on what we need. For example, one tool that I developed is a Trender, which its task is to calculate the trend in one specific feature, neighborhood feature, through all the time for all the postal codes that we have. Danny will show this for satellite greenness in the next presentation. We also interested to extract the values not only based on the locations, but based on the residential history of individuals that we have. So, for example, we are connecting our data to child cohort, and they have the residential history of their individuals, and we're interested in extracting the values based on the residential history, not just the location. And also, cohorts were wondering, what if, based on the features and values that we have, we can specifically find a postal code or one individual that has just this set of values and identify that participant. So to make sure that do we even have these cases, I've developed a tool that can identify postal codes with the unique combination of exposures that could lead to identifying a participant. This tool will identify unique combinations given list of variables and will tell us what postal codes have unique values. And we also provide the number of people at that postal code for the researchers, so that if the health data researchers want to censor the data, depending on the number of people, they can do that. And that was my presentation. Thank you.